Welcome back to the course on audio signal processing for music applications. In this week, we are talking about the DFT, and in this programming lecture, we're going to learn how to program it, how to implement the DFT equations in Python. In particular, we're going to talk both about the DFT equation, the direct version of the DFT, and the inverse DFT. In the DFT, we'll be computing all the x of k. So we'll be computing all the spectral values present in a given signal x of n. So we'll be iterating over all k and computing this sum. And in the inverse, we'll be iterating over all time over all n. And for each n, we'll be computing this sum. So let's start. Let's go to text editor, and we'll start by implementing the DFT. So the first thing we need to do is to import NumPy. Okay, that's our package for array processing. Now we have to initialize our output array of spectral samples. So we will create an empty array. Okay. Capital X, and we'll be now iterating over all frequency samples. So what we do is use the function range that basically creates values from 0 to n minus 1. So k now goes from 0 to n minus 1, and now we have to create the complex exponential at every frequency, at every k. So we'll create a complex exponential times 2 pi, okay, multiply by the frequency we want, and we need to divide by capital N, and then we need to create for all n. So we will create an array of time samples of indexes that will go from 0 to n minus 1. Okay, and that's a complex exponential at frequency k. And now we can compute the output spectrum, and we will do that by appending to the existing spectrum whatever was from the previous computation, and we will compute the sum of the input signal x by multiplied by the conjugate, okay, of our complex exponentials. So this is the inner product that we talked about in theory. And that's it. That's our DFT implementation. We can save it in a file. Let's call dft.py. And so this is a script that will run that. In order to see if it works, well, we need to put an input signal. So let's, before the code of the DFT, let's start using a particular signal. Let's define a signal of size n, and that will be equal to 64. And let's have a frequency that could be, for example, 7. Okay, and now we can declare the time signal as a, let's say, a complex exponential, and we will have a complex exponential that will be again 1j multiplied by 2 times pi. By the way, I left here also the NumPy package. Okay, 2 pi, and then we multiply by our frequency k0, our frequency index. We divide by n, and again we need to create an array of values so that we can compute n, capital N values of an input signal. And that's it. Now we compute the DFT, and we just, in order to see if it did anything, we just we will plot the result. In order to plot, we need to import the matplotlib, the pyplot, okay, pyplot, and we will call it PLT. Okay, and now in the plotting we will again do a time index being NP range capital N, and the spectrum, it's a complex signal, so we'll just plot the absolute value of it, and that should do it. And then we will have some axes so that they will go from 0 to n minus 1, and the horizontal axis will go from 0 to n. And that should do it. Now we just show it, and if we save it and we go to the terminal and we just type Python dft.py, okay, there is a problem. matplotlib dot there is a typo here, that pyplot, okay, that's better. Matplotlib, okay, here another typo, import. Another typo, okay, I made another mistake here, -1, and okay, that's it. So that's the DFT of a complex signal, and we see here that it's 64 at the location 7, and the rest is 0. So the analysis has proven that our input signal really was a complex sinusoid of value 7. Okay, now let's do it with real signals. So instead of having this complex sine wave, let's go to a real signal. So most of the code will be the same. So the only thing we have to do is change our input signal to be a cosine instead of being a complex exponential, which is the cosine, and we don't have the j. That should work. So this is our complex, our real signal, and we just save it and we compute it again. Okay, and now instead of having one peak, it has two. So a real signal has two complex exponential results. Is the sum of two complex exponentials, and we can visualize it here. Here the issue is that the axes are not so intuitive now, because it gives 7 and then this other value which is not, it should be -7. So a better way to implement this is instead of dealing with time index and frequency index going from 0 to n minus 1, it's good to go from -n/2 to n/2. So to do that, what we will be doing is create some array that will be quite used for different things. So will be NP range, and this will be going from -n/2 to n/2. Okay, and this is our time indexes, and also we will have frequency indexes that will be our k indexes. So now instead of computing from 0 to n, we will be computing in the DFT from -n/2 to n/2. So we'll iterate over k v, and in here again we will be in our time index, we will be nv, and hopefully that should work. And then of course in the axis we will have as output axis -n/2 to n/2 minus 1, and in here the plotting again will be over kv. Okay, so now well, there is another mistake here. in here I missed the over 2, over 2. Okay, and now, okay, this is better. So now we have centered around 0, and we have the -7 frequency and the 7th frequency. Okay, what happens if we do not have an integer value frequency? Instead of 7, we will have, let's say, 7.5. Okay, we save it, we run it, and, well, clearly it's very different. Now the projection of our input signal into the complex sinusoids of the DFT does not return a single value, but it's positive values for all complex exponentials. So that means that the projection has positive values for all the spectrum. Okay, and we explained this in the theory class. Okay, now we can do the inverse DFT, the equation that we also talked about and we showed in the slide. So now we will be implementing the inverse DFT equation. So we'll need to go over all samples of n and compute all these equations. So how do we do that? So it's quite similar to the DFT. So what we'll be doing is once we get the DFT analysis out, we will now create the inverse DFT code. So we'll first again initialize the output signal y with an array that will be an empty array. Okay, and we will be now doing a loop but over n. Okay, so we'll be doing over n in nv, and we will have to compute the complex exponentials, but they're going to be a little bit different, because now here the complex exponential is 1j multiplied by 2 multiplied by np dot pi, and in here instead of multiplying by all for every k, we'll do it for every n divided by n, and here we will have an array of frequencies of kv. So this way, this basically s is the sum of all complex exponentials of all possible frequencies at a given sample. And now the output will be, again we will keep appending the output samples, and we will be appending to the y sample the sum of the spectrum x by the s, which are the complex exponentials. And that should do it. This should compute the inverse DFT. While we are missing something, in there was 1 over n and multiplied, which is the normalization factor of the inverse DFT. And now to plot, what we're going to plot is we're going to plot for all samples, we're going to plot the output signal y, and the axis will go again from minus n over 2 to n over 2 minus 1, but being a time signal, it's going to go from minus 1 to 1. And that should do it. Hopefully, if we execute this, okay, there is a problem of k here. We typed kn, which is kv. Okay, and now if we run it, okay, this is the output signal y. So at time 0 is a cosine, so this was a cosine function, and it has 7.5 periods of our signal. That's the input signal we had, and this is exactly the same than the output signal we have computed. And that's all I wanted to say. So basically in this class we have implemented the DFT and the inverse DFT equations. So please make sure that you understand those equations. And of course we have been using complex sine waves, the DFT sine waves, to implement that. And in the coding, we needed 2 packages, the NumPy and the Matplotlib, and that's it. So we have hopefully completed the DFT explanation. We talked about the theory part, we made some demonstrations, and now in this programming class we have been able to actually implement it. And of course this is not all, this is just the very beginning. It's going to get a little bit more complicated, but please hang on, and hopefully I will see you next week with more advanced topics. Thank you very much.